All right, let's dive into one of the most successful and, honestly, one of the weirdest theories in all of science. I'm talking about quantum electrodynamics, or QED for short. Now, to really get a grip on its power, we're not going to start with something crazy like black holes. Nope, we're going to start with something you see every single day, a simple sheet of glass.
Okay, so here's a basic fact we all know. When light hits a piece of glass, some of it reflects, right? It's about 4% to be precise. You see this in your window every single day. But, and here's where things get really strange, what happens if you put a second, super thin pane of glass right behind the first one?
Now, common sense would tell you, okay, two surfaces, 4% each, that's 8% reflection. Simple math. But when you actually go and do the experiment, reality just laughs at your common sense. Because depending on how thick that glass is, the reflection can be anything from 0%, I'm not kidding, zero reflection, all the way up to a whopping 16%. Think about that. That second piece of glass can either completely erase the reflection or make it 4 times stronger.
So, your brain is probably already racing, trying to come up with a normal explanation. Maybe there are tiny little reflective bits like specks on the glass. Nope, Newton shot that idea down centuries ago. Okay, what if the second surface somehow sends a secret message back to the first one, telling it what to do? I mean, how would that even work? Or maybe the photons themselves have little internal gears or something? Nah, that doesn't fly either. The bottom line is every logical, mechanical explanation you can come up with, it just completely falls apart.
To get to the real answer, we have to do something radical. We have to take our common sense and just toss it right out the window. Instead, we're going to follow a set of rules from the legendary physicist Richard Feynman. And here's the kicker. He himself admitted his theory was absurd, but it had one incredible thing going for it. It was always right, no exceptions.
So what is this big secret? Well, it all boils down to this wonderfully weird concept called a probability amplitude. And don't worry, forget about all the scary, complicated math. To do quantum mechanics the Feynman way, all you really need is a piece of paper and a pencil to draw little arrows. Seriously, that's it. This tiny arrow is going to represent the chance of something happening.
And there are only 2 rules you need to remember. They're simple, but they're weird. Rule number 1, the actual probability, the real chance of something happening, is the length of your final arrow squared. So if your arrow has a length of, say, 0.2, the probability is 4%. Easy enough. Now, rule number 2, and this one is absolutely key. If an event can happen in more than one way, you have to draw an arrow for each and every one of those ways, and then you just add them up, tip to tail, to get your final arrow.
Okay, you've got the rules. Let's put them to the test. How on earth can drawing a couple of silly arrows solve our mystery with the glass? How can this explain reflections that vanish or get supercharged?
Well, remember Rule 2? If something can happen in more than one way, you add the arrows for each way. So let's think about our photon. How can it get to our eye? Well, there are 2 ways. It could hit the front surface of the glass and bounce right back. Or it could go through the glass, hit the back surface, and then bounce back out. See? 2 possible paths. So that means we need 2 arrows.
And boom, here's the magic. For a really, really thin piece of glass, it turns out the arrow for the front surface reflection and the arrow for the back surface reflection point in exactly opposite directions. So when you add them tip to tail, they completely cancel out. Your final arrow has a length of 0. And what's 0 squared? 0. No reflection. It's gone. But now watch this. If you make the glass just a tiny, tiny bit thicker, that extra distance the second photon has to travel actually causes its arrow to rotate. And at just the right thickness, boom, the 2 arrows are pointing in the exact same direction. You add them up, you get one big arrow that's twice as long. You square that, and you get 16% reflection. It's all about the direction of those arrows.
And this is where your mind should be a little bit blown. Because this whole adding arrows thing, it's not just some clever trick for a single puzzle about glass. No, this turns out to be one of the deepest, most fundamental rules of how our universe actually works.
Think about it. This exact same method explains why light seems to travel in straight lines. It explains why a mirror reflects light at the same angle it comes in. It explains how a lens in a camera focuses light. It even explains those beautiful shimmering colors you see on a soap bubble or in a puddle of oil. All of these things we see every day are all happening because of this one simple but totally bizarre quantum rule. What we've just been talking about
This is the heart of quantum electrodynamics. It's our best, most complete understanding of how light and matter, how photons and electrons actually interact. And when I say best, I mean the accuracy is just, well, it's absolutely staggering.
Let me show you the raw power of this idea. Using QED, physicists can calculate a very specific property of the electron. It's called its magnetic moment. And after doing all the math, which is basically a very, very complicated version of adding arrows, the theory predicts the value should be this number right here.
So, that's the prediction. What happens when we actually go into a lab and measure it? Well, the experimental result is this number. Just look at those two numbers. They are basically the same. The theory and reality match up perfectly all the way down to the 10th decimal place. It's just unbelievable.
To help you really grasp what that level of accuracy means, Feynman came up with the perfect analogy. He said that this agreement between theory and experiment is like measuring the distance from New York City all the way to Los Angeles and getting it right to within the width of a single human hair. That's how good this theory is.
So, here's the big takeaway. QED, it's not just another theory. It is the single most successful, most precisely tested theory in the entire history of science. It just works flawlessly. Now, do we have a good common sense reason for why the universe works this way? Why it's all about adding little arrows and squaring their length? No, not really. But we absolutely cannot deny the fact that it does.
And that brings us right back to what Feynman said. He basically told us we just have to accept nature for what she is, which is, from our point of view, completely absurd. Our job as scientists isn't to make sure theories feel cozy and make sense to us. Our job is to check if they match what we see in experiments. And QED does that better than anything we've ever come up with.
And this leaves us with a really deep, kind of unsettling question, doesn't it? The world we experience every day, the world that seems so solid and predictable, is built on a foundation that is just fundamentally bizarre. It's all about probabilities and weird rules that defy all our instincts. So if our most successful, most accurate theory of reality is something that our common sense finds absurd, what does that really say about the limits of our own intuition? What is the universe trying to tell us?